Hello, everyone. This is Jeff Wilkerson, professor of physics at Luther College. We have a series of videos out there on how we use KaleidaGraph to process data a little bit in both the classroom lab setting and in the research lab setting somewhat. And what we're going to work with today is identifying residuals from curve fits in KaleidaGraph and look at some straightforward, there are different ways you could do this, but we're going to look at some straightforward ways to think about doing this work. So I'm going to share my screen with you and look at some data. We're going to do a curve fit, and then we're going to look at the residuals of the data from that curve fit. So let me go in and share with you my KaleidaGraph window here. So you can see what we've got here. All I did was, this is a variable star that we have, a long period pulsating variable star that we've been looking at for 20 years. This is 1 year of data cut out. This is a Julian date, a mean Julian date in this column, and this is the magnitude that we measured in our data set. You'll see we have a data masked out that didn't pass our photometric quality tests in this particular year. And I'm just going to make a scatter plot like I like to do. We'll put the date on the x-axis and the magnitude on the y-axis, and we plotted that up there, and it all looks good. We would clean this up, get rid of the title, and change the numbering here on the labels on the axes, and get rid of this legend and stuff like that, but we're not going to worry about it. Note that this is a fairly low amplitude variable star. It's got a nice clean variability this year, but we're talking about hundredths, maybe to tenths of a magnitude of variability, which is pretty low amplitude for these long period variable stars. And so you get these points that look high, that look like they might just be noise, but you get something like this that's low for several days in a row, and that actually looks like the bottom dropped out of that star for a while. And we might want to explore that. And one way we might explore it is to do a curve fit. So I'm going to do a second order polynomial curve fit. It comes up as second order right there. You see the 2. We could change it to 3 or 4. But we want to just do a second order polynomial curve fit. Understand, we have this is not a meaningful curve fit. We're not saying we think that these data are actually related by a second order polynomial. This is an empirical curve fit where we're just trying to see if we can fit the data okay. And it turns out we don't fit the data great. You see that we miss up here. But it does tell us that we've got this point where all of these points do seem to be low, and we can start to get a sense of what that this might be a region we want to explore to find out why these were all below that fit. So one way to do that is to come in here, and I'm going to say, I'm going to go back up here under curve fit, and I'm going to pull down on my curve fit, and you see this little arrow under view. It's a handy arrow to say, let's copy the predicted values to the data window. We did that. Now it says this is our fit values. We could go to the formula entry window, and we could take a difference between these two values, and that's our residual. That tells us how much we missed the fit, and the data were different at that given date across there. But we're going to do that a different way. I'm actually going to do it by making the graph again, just so you see me walk through the graph a second time, magnitude, and say, okay, let's plot that. Just what we had before. We're going to do the curve fit again, so you watch that again, second order polynomial, boom, boom. Okay, so we got a nice quick fit right here. And this time I'm going to go back to the curve fit, and I'm going to pull down under here on residuals. And to say, what does it say? Copy the residuals to the data window. And there you see it wrote them in. 0.05, that's the difference. That's the fit value minus the data value. I could have maybe would have done that the other way. I don't know, but that's the difference between these two, what we got in a fit and what we got from our data. And then I could go back up here if I want to, and I can make another scatter plot and say, why don't I look at the residuals as a function of date and see what's going on, see if there's anything interesting there. And maybe that's interesting. You know, again, I don't think this was a meaningful fit physically, but you've got this sort of a little bit of a pattern here that suggests you got these noise spikes in here, but it suggests that these are the points where we were missing, the fit was missing high. And you see that we walked right into that So it tells me that it gives me an idea of sort of what's going on with these fits around here and areas that I want to explore. I'm not making any real physical meaning out of this. I'm just saying this is great to do. But mostly what we're interested in here today is to see how easy it is. You could. You could have gone about this a completely different way. You could have said, hey, I want to find out what my fit was at this date. I could have taken the formula from the fit right here, and I could have written it in the formula entry window, do a control F, and there the formula entry window shows up. And I could have written that in here to say, hey, let's do that. Let's say C5, it's not hard this way. C5 is equal to these fit parameters down in here. And to say, so actually, let's try this. Yeah, okay. To say M0 is minus 222.32. Oh, wait. We could do it that way. No, let's do it. Let's do it by hand. Just to show you, this is sort of the extreme other end of the way we could do this. Is we could say C5 is equal to minus 222.32. And M1 times X is going to be plus 0.08184 star whatever our X value is. That's over here. That's C0. And then we've got minus 7.079 east. Let's just put it in that way. 7.0937 e to the minus 6. So not very big at all. Star C0 squared. And that should work for us. Let's try it. Oh, we're not in there. And we've got our fit parameters out here. I got some round off error you see right here. But we get our fit parameters out in here where I presumably typed something in not quite the same as what was out there. But that's the other way to go about doing this, right? That is the other way to go about just typing this in. And that didn't take us that long to do. We could certainly get away with that. But the point of this video was to show you how slick it was to find the residuals and the fit values if this is what we were trying to do, and to write them in here and to save this whole thing. And then we could compare a bunch of fits. I could go now and say, what if I wanted to take, let's just start again. Let's just make a new plot and put the date on the x-axis and the magnitude on the y-axis and plot that. And now I'm going to go back over here and I'm going to say where it says fit values right there. Good grief, my typing is terrible. I'm going to call it poly2 fit values. So that's my second order polynomial fit values. And I'm going to come out here and I'm going to say, let's do another fit. Well, I don't know what kind of fit we want to do. Let's do, see what we got here. Let's do a Gaussian. Okay, and so let's define that Gaussian. Let's say 13. Let's do an offset of 0.1. I don't know what that offset wants to be. Mostly I shouldn't be doing this on the fly. M2 is the scale height out here, so let's make that 13.75. Not terribly sensitive to these values. Outside the exponential is sensitive to the values inside the exponential. So let's make that 5820. Let's make it 5805. That's our mean value. That's the mean value in x right here, you see. So I'm going to go 5805. And then the standard deviation across here. This is noisy. I don't know if it's going to fit at all or not. But I'm going to make the standard deviation across here be about 55. Okay, and let's see if we did okay fitting it. Oh, we did. Okay, so there's a Gaussian fit that we got. Now, I don't know if I like that Gaussian or not. You see the points that we were looking for, this is still low. So it's still whatever we try to fit. Now I could try a whole bunch of different fits, and this could become a student research project for a long time. We can start to try to understand what's going on here and try other variable stars to say, is this a data calibration problem? Because we have other variable stars that are missing their fits on these nights, their smooth trends on these nights. But anyway, just what I want to show you here is I can go up here to the curve fit, and I can go back to general and Gaussian, and I got the same little box. And let's see what happens if we try to copy the predicted values to the data window. There it is, bam! There's the fit values. And I can say, okay. And so now this is fit values. Oh, it copied the same fit values from before. That's an interesting thing for us to go back and look at. So we could try to copy the fit values down in here to see what we're getting. Now there's an interesting exploration. Do we want to try to clear all of this out and just start from scratch and see what happens with what we have going on here? Because it seemed to not replace the fit values that it had before here. Interesting places for us to explore. I'm not going to explore it here live while you are. I'm not going to explore this live here while you're watching. We'll do more a little bit later, but hopefully that's helpful for you to think about how you can use the fit values and the residuals in your KaleidaGraph curve fits. So thanks for watching, everybody. We'll have more for you some other time in the future.